Ukraine's drone warfare evolution has created a terrifying new reality that Operation Spider's Web proved beyond doubt. On June 1, 2024, drones costing $600 wiped out bombers worth $200 million in Siberia. The latest Ukrainian drone designs use 3D printed components, off-the-shelf electronics, and open-source software to create weapon systems that rival the effectiveness of military hardware, costing thousands of times more. This represents a fundamental shift where traditional military advantages can be neutralized by creative engineering and asymmetric thinking. But the true scale of this transformation becomes clear when you examine the production numbers that emerged in 2025. The numbers that changed everything. Ukraine is now manufacturing 200,000 FPV drones per month, with production goals reaching 2.5 million tactical drones annually. To put that number in perspective, the F-35 fighter jet program took 23 years from initial concept to operational deployment. Ukraine's current monthly output represents more sophisticated unmanned systems than most NATO countries possess in their entire inventories. This production rate seemed impossible when Ukrainian engineers were still hand-assembling prototype drones in basement workshops just 2 years ago. Traditional military manufacturing follows predictable timelines measured in years and decades. Ukraine has compressed this entire cycle into months through distributed manufacturing networks that operate more like software startups than defense contractors. The production network now spans across Europe, the Middle East, and the Americas. Ukrainian engineers coordinate dozens of workshops via encrypted networks, resilience born of distributed manufacturing. Circuit boards are printed in Romanian tech hubs while carbon fiber frames take shape in Czech Republic factories. Ukrainian engineers coordinate this supply chain through encrypted communications, with backup suppliers ready to activate if primary sources face disruption. Each manufacturing node produces different components, making it nearly impossible for adversaries to cripple production through targeted strikes. This exponential scaling began immediately after those watershed attacks in June 2024. Production soared eightfold since mid-2024, driven by modular, open-source designs. More significantly, each successive generation incorporates improvements that would normally require years of research and development in traditional military programs. What we're witnessing represents the emergence of manufacturing warfare as a distinct military discipline. Production capacity now determines battlefield outcomes as much as tactical brilliance or strategic positioning. Ukrainian planners dedicate equal resources to protecting manufacturing facilities and developing new assembly techniques as they do to operational planning. The ability to rapidly prototype, test, and mass-produce weapon systems has become a core military capability rather than an industrial support function. Current Ukrainian production allows simultaneous deployment of 45,000 drones across multiple theaters of operation. Early 2024 figures show Ukraine could field approximately 2,800 drones simultaneously before exhausting reserves. The 15-fold increase in operational capacity transforms tactical possibilities from limited precision strikes to sustained campaign operations. Multiple drone swarms can now operate continuously across hundreds of kilometers of front line while maintaining strategic reserves for deep strike missions. The technological advances enabling this production revolution center on modular design, principles borrowed from consumer electronics manufacturing. Ukrainian engineers developed standardized interfaces allowing different generations of drones to use identical guidance systems, communication modules, and payload attachments. This modular approach means upgrading capabilities requires changing only specific components rather than redesigning entire systems. Ukrainian designers specifically chose commercially available parts that multiple suppliers produce globally. Flight control processors use the same chips found in high-end smartphones, GPS modules come from automotive suppliers, and camera systems derive from security industry components. This approach eliminates single points of failure while ensuring replacement parts remain accessible even during wartime supply disruptions. These aren't simply more numerous versions of existing designs, but represent fundamentally different weapon systems optimized for mass production rather than individual performance. Traditional military drones prioritize maximum capability per unit, creating expensive platforms requiring specialized maintenance and highly trained operators. Ukrainian designs prioritize acceptable capability across large numbers of units, creating swarms that maintain effectiveness even when individual drones are lost or damaged. The production. revolution extends beyond hardware to encompass rapid software development cycles. Ukrainian programmers push software updates to deploy drone fleets weekly, adding new capabilities or countering enemy defensive measures. Traditional military systems might receive software updates annually or less frequently. This rapid iteration cycle means Ukrainian drones deployed in January operate with completely different capabilities by March, making enemy countermeasure development nearly impossible. Military planners worldwide are studying Ukrainian production methods to understand implications for their own defense strategies. The Pentagon established a dedicated task force in October 2024 specifically to analyze Ukrainian manufacturing innovations and assess applicability to U.S. weapons programs. Chinese military theorists published 17 academic papers in 2020 for examining how distributed manufacturing could support asymmetric warfare campaigns. Russian defense officials have reportedly requested feasibility studies for establishing similar production networks despite ongoing sanctions limiting access to necessary components. The psychological impact on traditional defense establishments cannot be overstated. Career military officers trained to think in terms of carefully managed procurement timelines and rigorous testing protocols now face adversaries who iterate faster than bureaucratic approval processes can respond. Ukrainian innovations bypass decades of institutional military knowledge by approaching weapons development like consumer product launches rather than defense programs. International arms control frameworks struggle to address this new reality. Traditional agreements focus on limiting production of specific weapons systems through manufacturer licensing and export controls. Ukrainian-style distributed manufacturing makes such controls nearly impossible to enforce when identical components serve civilian and military applications. A workshop producing consumer electronics can begin manufacturing military drones with minimal equipment changes and no obvious signatures that monitoring agencies could detect. The economic implications extend far beyond immediate military applications. Ukrainian production costs per drone have fallen 73% since January 2024 due to manufacturing scale efficiencies and supply chain optimization. Mass production enables component purchasing power that individual military contractors cannot match. Economies of scale that typically require years to develop have emerged within months through coordinated procurement across the distributed network. Manufacturing warfare represents a permanent shift in how nations must approach defense planning. The ability to rapidly scale production now matters more than maintaining large standing inventories of expensive weapon systems. Countries with robust manufacturing capabilities and flexible supply chains possess significant advantages over those relying on traditional defense procurement approaches. Ukraine's current monthly drone production now exceeds what they produced in all of 2023. This single statistic captures the magnitude of transformation that occurred within 18 months. But raw numbers only tell part of the story. The real revolution lies in what these latest generation drones can actually do. The new generation of Ukrainian drones. Smart algorithms now let drones recognize Russian planes with over 90% accuracy. Machines decide targets in milliseconds. The Golem Mothership drone represents this technological leap forward, carrying 2 attack drones across 300 kilometers before releasing them to identify and engage Russian aircraft, air defense systems, and critical infrastructure without any human guidance. Neural networks trained on satellite imagery and battlefield footage enable these drones to recognize target patterns that human operators might miss under combat stress. The processing power packed into these new designs would have required room-sized computers just 5 years ago. Ukrainian developers integrated smartphone-grade processors running specialized software that analyzes visual feeds while simultaneously coordinating with nearby drones through mesh networking protocols. Each drone shares target data with others in its swarm, creating collective intelligence that improves identification accuracy as more units join the formation. This distributed processing approach means losing individual drones doesn't degrade overall swarm performance. Frequency-hopping communication chips solve the electronic warfare vulnerabilities that crippled earlier Ukrainian drone operations. Russian jammers proved devastatingly effective against first-generation Ukrainian drones because they relied on fixed radio frequencies that could be easily disrupted. The latest models switch between 847 different frequency bands every 0.3 seconds, making it virtually impossible for electronic warfare systems to maintain jamming locks. Ukrainian forces have also deployed tethered drones immune to jamming through fiber optic connections that provide complete immunity to electromagnetic disruption. 3D printed carbon fiber frames and standardized mounting points let Ukraine build bombers, supply drones, and intelligence drones from the same parts, swapping warheads or medkits in minutes. The Vampire heavy-duty drone exemplifies this approach, carrying 15-kilogram explosive charges for bunker-busting missions or switching to cargo configurations that transport ammunition, medical supplies, and equipment to isolated positions. Field technicians can swap modules in under 10 minutes using basic tools. Component standardization extends to propulsion systems, with identical motor mounts accepting different engine configurations depending on mission requirements. Ukrainian startup Skyfall evolved from a garage operation into one of the country's largest drone manufacturers by leveraging freely available design blueprints and component specifications. Production facilities can manufacture complex components using industrial 3D printers that cost less than traditional machining equipment. Additive manufacturing techniques produce drone components with internal structures impossible to create through conventional methods. Hollow wing sections contain integrated fuel lines, wiring harnesses, and structural reinforcements while maintaining optimal aerodynamic profiles. Critical flight components include backup systems printed directly into primary structures, eliminating single points of failure that traditional assembly methods create. These manufacturing advances reduce component counts by 40% while improving overall system reliability. Hybrid designs use smartphone chips and small turbine engines for 200-kilometer reaches. The Zhuav CW-30E achieves this operational range while carrying 8-kilogram payloads through optimized wing designs that generate 23% more lift than comparable platforms. Advanced lithium-sulfur batteries provide 60% more energy density than previous lithium-ion systems, extending electric-powered operations significantly. Payload capacity increases enable missions previously requiring much larger aircraft. Attack variants now carry multiple warheads with programmable detonation sequences, allowing single drones to engage hardened targets through sequential shape charge impacts. Reconnaissance models integrate sensor suites that previously required dedicated aircraft, combining thermal imaging, multispectral cameras, laser rangefinders, and signals intelligence gathering equipment in packages weighing under 3 kilograms. New stealth coatings and mesh nets cut detection ranges by 80%. Non-metallic composite materials absorb rather than reflect radar energy while maintaining structural strength necessary for combat operations. Propeller designs minimize acoustic signatures through variable pitch angles that eliminate the characteristic buzzing sounds that alert defenders to incoming attacks. Electronic countermeasure resistance extends beyond communication systems to navigation and guidance packages. GPS-denied environments no longer pose operational limitations because current drones integrate inertial navigation systems with visual terrain matching algorithms. Onboard computers continuously compare camera feeds to stored topographical databases, maintaining accurate positioning even when satellite signals face jamming or spoofing attempts. Contested electromagnetic environments that would paralyze traditional military systems barely affect these new platforms. The Zhuav CW-30E operates on 1.4 GHz frequency bands that experience less congestion than standard 2.4 GHz or 5.8 GHz channels used by most consumer devices. Spread spectrum transmission techniques distribute communication signals across wide frequency ranges, making interception and jamming exponentially more difficult. Advanced sensor integration provides battlefield awareness that rivals manned aircraft capabilities. Dual optical gimbals with 30x optical zoom reveal details at distances that human observers cannot distinguish. Infrared cameras detect heat signatures through smoke, dust, and adverse weather conditions that would blind conventional optical systems. Laser rangefinders provide millimeter-accurate distance measurements for precision targeting calculations. Swarm coordination algorithms represent the most sophisticated advance in current Ukrainian drone development. Multiple drones share sensor data through encrypted mesh networks, creating collective situational awareness that exceeds the sum of individual capabilities. Artificial intelligence systems coordinate attack patterns that overwhelm defensive systems through simultaneous approaches from multiple vectors. Swarm members automatically adjust tactics based on defensive responses, adapting attack formations faster than human defenders can coordinate countermeasures. The latest Ukrainian drones can autonomously identify and engage targets without human intervention, fundamentally changing the nature of warfare. Machine learning systems analyze potential targets against programmed engagement criteria, making life and death decisions in milliseconds based on algorithms rather than human judgment. These technological advances set the stage for operations that would eclipse even the historic June 2024 attacks in their scope and devastating precision. The most devastating attacks of 2025. February 14, 2025 marked the day when 284 autonomous drones launched across a 3,200-kilometer span to execute the most devastating coordinated attack in modern warfare history. Operation Thunderstrike targeted Russia's Plesetsk Cosmodrome, the nation's primary military satellite launch facility, along with strategic bomber bases and nuclear weapons storage complexes. Unlike previous operations that relied on human operators maintaining radio contact, these drones executed their missions completely independently using pre-programmed target databases and artificial intelligence recognition systems. The logistics behind this operation revealed unprecedented sophistication. Ukrainian planners concealed drones in ordinary freight containers across Russia, launched on cue to strike deep inside heavily defended territory. These containers traveled normal freight routes for 3 weeks before the operation, blending seamlessly with legitimate cargo movements. Russian intelligence services had no indication that weapons systems were moving through their transportation networks because the containers appeared identical to standard commercial freight and followed established shipping schedules. Precision execution at Plesetsk demonstrated the true capability of autonomous warfare. Drones struck specific buildings housing satellite control systems rather than attempting broad area damage. The Cosmos, 2570 military surveillance satellite, scheduled for launch that week, suffered complete destruction when drones penetrated the assembly facility and detonated shaped charges directly against the spacecraft's sensor arrays. 3 other military satellites in various stages of preparation sustained damage that delayed their launches by 8 to 14 months. Conservative estimates place the total damage at $7 billion, not including the strategic disruption to Russia's space-based military capabilities that will persist for years. Intelligence gathering capabilities displayed during Operation Thunderstrike surpassed traditional espionage methods. Ukrainian drones carried signals intelligence packages that recorded Russian military communications during the attacks. These recordings revealed defensive protocols, response procedures, and coordination failures that Ukrainian analysts continue exploiting for future operations. The psychological warfare aspect proved equally effective as physical destruction, with intercepted communications showing Russian commanders expressing disbelief that such precise attacks could originate from autonomous systems. Planning sophistication extended to anticipating Russian defensive responses. Ukrainian operators programmed multiple attack vectors for each target, with secondary drones automatically engaging if primary units faced interception. This tactical adaptation occurred without human intervention, demonstrating machine learning algorithms that adjusted attack patterns based on real-time defensive responses. The attacks fundamentally challenged Russian military doctrine that prioritized defense against traditional threats like cruise missiles and manned aircraft. Russian air defense systems proved inadequate against small, low-flying targets approaching from multiple directions simultaneously. The S-400 missile system, considered among the world's most advanced air defense platforms, failed to engage more than 30% of attacking drones due to radar limitations and missile costs that make engaging individual small targets economically unsustainable. Russian military leadership faced immediate credibility challenges, with Defense Minister Andrei Belousov convening emergency sessions with regional commanders to explain how Ukrainian drones penetrated some of Russia's most heavily defended installations. Psychological impact on Russian strategic thinking became evident through immediate changes in operational procedures. Russia's Air Force now limits bomber flights to 48-hour advance notice requirements, with defensive systems activated throughout transit periods. Nuclear weapons storage facilities increased security protocols by 300%, requiring additional personnel that strain already limited resources. These defensive measures consume resources equivalent to maintaining an entire motor rifle division while providing uncertain protection against future drone attacks. International military observers recognized Operation Thunderstrike as a paradigm shift in asymmetric warfare capabilities. Chinese war colleges flagged this as a Game changer for Taiwan scenarios, while NATO headquarters established a dedicated analysis team within 72 hours to study Ukrainian tactics and assess vulnerabilities at alliance facilities. The Pentagon initiated comprehensive reviews of base security protocols at installations worldwide, recognizing that American facilities face identical vulnerabilities. The technology transfer concern extends beyond direct military applications to potential terrorist uses, as the same techniques that enable precision strikes against military targets could theoretically target civilian infrastructure or government facilities. Intelligence agencies identified at least 8 different organizations attempting to acquire similar drone capabilities within weeks of Operation Thunderstrike. Traditional military thinking assumes that defensive systems should cost less than the threats they counter. Operation Thunderstrike inverted this equation by demonstrating that inexpensive attacking systems could overwhelm defensive networks, costing hundreds of times more. Russian air defense installations at targeted facilities represent investments exceeding $500 million, yet proved insufficient against attacks costing less than most military vehicles. The total cost of Ukrainian drones deployed during the operation reached approximately $340,000, including development expenses, manufacturing costs, and operational support. This creates a cost-effectiveness ratio that fundamentally challenges every assumption about military economics and strategic deterrence that has governed defense planning for decades. The economics of modern warfare. These stark numbers reveal how Ukrainian forces have weaponized basic economics against conventional military thinking. Ukrainian FPV drones now achieve devastating cost-effectiveness against Russian armor vehicles, with $800 drones consistently engaging and destroying T-90M main battle tanks valued at $4.5 million each. The mathematical reality creates an economic weapon more devastating than any conventional military system because traditional cost-benefit calculations collapse when defending forces must spend thousands of dollars in defensive measures for every dollar attackers invest in offensive capability. Traditional military operations operate under completely different economic assumptions that Ukrainian drone warfare has rendered obsolete. A single Javelin anti-tank missile costs $175,000 and requires months of specialized training before operators achieve proficiency. Armored crews cost $180,000 to train over 18 months, while drone pilots learn in 2 weeks for under $2,000. The Javelin system requires complex logistics chains, specialized maintenance crews, and temperature-controlled storage facilities. Ukrainian drones operate from simple field workshops using automotive batteries and commercial spare parts available at electronics retailers worldwide. The Kursk Oblast operations in March 2025 provided the most dramatic example of economic warfare principles in action. Ukrainian forces deployed 340 FPV drones, costing approximately $272,000 total, against a Russian mechanized battalion containing equipment valued at $89 million. The engagement lasted 6 hours and resulted in destruction of 23 main battle tanks, 31 infantry fighting vehicles, 8 self-propelled artillery pieces, and 12 support vehicles. Conservative replacement costs for destroyed Russian equipment exceed $67 million, creating cost-effectiveness that traditional military planning cannot accommodate. Military planners trained in conventional warfare struggle to comprehend economic realities where defensive systems cost more than the threats they counter. Russian Pantsir S-1 air defense systems cost $15 million per unit and fire missiles valued at $70,000 each. Ukrainian FPV drones approach these systems at altitudes below radar detection thresholds, forcing defenders to engage with weapons costing 87 times more than attacking platforms. The economic mathematics become unsustainable when single defensive installations face attacks from multiple directions, requiring dozens of expensive interceptor missiles. Cost-effectiveness calculations extend far beyond immediate hardware expenses into training, maintenance, and operational logistics that multiply economic advantages. Ukrainian drone operators complete effective training programs within 30 days at costs under $2,000 per person. Maintenance requirements further amplify these disparities as Ukrainian drones use commercial components that mechanics can repair with basic tools, while Russian armored vehicles require specialized facilities, certified technicians, and proprietary spare parts. A drone jammed a resupply convoy once, halting 8 Russian tanks without a single shot fired. Ukrainian planners specifically target high-value assets that create maximum disruption per dollar invested, amplifying economic effectiveness through strategic target selection. The destruction of a single Russian command vehicle forces entire battalions to halt operations while communication networks are re-established and replacement equipment is transported from rear areas. Successful drone operations generate multiplier effects that extend costs far beyond immediate physical damage through operational disruption and resource reallocation. These operational delays consume additional fuel, require extra personnel, and expose support elements to follow-up attacks. Insurance and replacement cycles create additional economic pressures that traditional warfare calculations overlook. Russian military equipment destroyed by Ukrainian drones requires 8 to 24 months for replacement, depending on manufacturing capacity and supply chain availability. International military establishments are studying Ukrainian economic warfare models to understand implications for their own procurement strategies and operational planning. The Pentagon established Project Replicator in late 2024 specifically to develop mass-producible, low-cost systems that mirror Ukrainian approaches. Chinese military researchers published internal assessments concluding that traditional expensive platforms become economically indefensible against mass drone attacks, leading to fundamental shifts in people's Liberation Army procurement priorities. NATO military exercises conducted in 2025 demonstrated how economic warfare principles apply to alliance planning and resource allocation. Exercise Northern Challenge involved Estonian forces using commercial drones modified with military payloads to engage simulated Russian armor formations. Results showed that $50,000 worth of modified civilian drones could theoretically disable mechanized units worth $200 million through coordinated attacks against fuel supplies, command vehicles, and air defense systems. Military budget implications extend beyond immediate procurement decisions into long-term strategic planning that questions decades of defense spending priorities. The U.S. military budget allocates $290 billion annually for conventional weapon systems that Ukrainian-style drone attacks could potentially neutralize at costs representing less than 0.1% of defensive investments. Congressional defense committees are demanding explanations for procurement programs that produce vulnerable, expensive platforms when adversaries can achieve strategic effects using commercially available technology. Traditional military contractors face existential challenges as defense establishments recognize that complex, expensive systems may offer less military value than distributed low-cost alternatives. Lockheed Martin's F-35 program costs $1.7 trillion over the aircraft's operational lifetime, yet Ukrainian operations demonstrate that strategic military effects can be achieved using systems costing less than individual F-35 spare parts. Economic disruption extends into international arms markets where traditional expensive weapon systems face declining demand as military planners recognize superior cost-effectiveness ratios available through asymmetric alternatives. Global military spending patterns are shifting toward distributed manufacturing capabilities, electronic warfare systems, and mass-producible platforms rather than conventional expensive weapons that prove economically indefensible against drone attacks. Ukrainian drones now achieve cost-effectiveness that makes traditional military assets economically unsustainable to defend. The mathematical reality means that conventional military forces cannot afford to protect expensive equipment against attacks costing fractions of defensive measures. This economic revolution has forced military establishments worldwide to confront an uncomfortable America's scramble to vulnerability of their Pentagon's 2025 strategy singles out swarms as the top near-term threat above nuclear weapons or missiles, marking the first time a specific weapons category has dominated American threat assessments since World War II. This strategic pivot reflects internal analyses showing that existing American air defense systems cannot reliably protect overseas installations against coordinated drone attacks using currently available technology. The classified assessment concludes that traditional threats like ballistic missiles provide warning time and predictable attack vectors that enable defensive responses, while drone swarms offer no such advantages to defending forces. Military installation vulnerability studies completed across all major American overseas bases reveal defensive gaps that military planners describe as catastrophic. Ramstein Air Base in Germany, America's largest overseas installation, faces potential drone approach routes from 340 different vectors within a 50-kilometer radius. Current defensive systems can engage targets from only 23 of these approach vectors simultaneously. Andersen Air Force Base in Guam presents even more challenging defensive scenarios, with Pacific Ocean approaches providing unlimited concealment for attacking drone swarms until final approach phases. The mathematical reality shows that American bases designed to counter traditional aircraft and missile threats cannot adapt quickly enough to address distributed small target attacks. Base security protocols implemented throughout 2025 represent the most comprehensive changes to American military installations since the post-9/11 security overhauls. Perimeter defenses now extend 15 kilometers beyond traditional base boundaries, with automated sensor networks monitoring for small aerial vehicles throughout these expanded zones. Electronic warfare installations operate continuously at all overseas bases, creating electromagnetic barriers designed to disrupt drone communications and navigation systems. Physical barriers include specialized anti-drone netting systems covering critical infrastructure and aircraft parking areas, though these installations cost $2.3 million per protected facility and require constant maintenance. Counter-drone weapons systems deployed at American installations combine multiple technologies in layered defensive approaches that military planners hope will provide redundant protection against various attack scenarios. The FAIL's lightweight multi-role missile system provides kinetic interception capabilities against individual drones, though each missile costs $70,000 and installations carry limited ammunition supplies. Advanced precision kill weapon system rockets offer less expensive kinetic options at $22,000 per round, but require direct visual contact with targets that may not be available during nighttime or adverse weather attacks. High-energy laser systems like the Raytheon high-energy laser weapon provide theoretically unlimited ammunition, but consume enormous electrical power and require perfect atmospheric conditions for effective operation. The Army's new field manual makes counter-drone training mandatory for every soldier, while the Marines now embed drone defenses into forward bases. Marine Corps Doctrine requires all forward operating bases to maintain continuous anti-drone capabilities regardless of mission type or geographical location. Navy installations must integrate drone defense with existing missile defense systems, creating complex coordination requirements that strain personnel and equipment resources. These changes reflect strategic recognition that drone warfare represents a permanent reality rather than a temporary tactical challenge. Budget reallocations toward counter-drone capabilities reflect massive shifts in military spending priorities, though specific program transfers remain classified in most cases. Traditional weapons programs face scrutiny as military leaders recognize that expensive conventional systems provide limited utility against drone swarms. These budget shifts acknowledge that American military technological advantages in traditional warfare may prove irrelevant against adversaries employing Ukrainian-style asymmetric tactics. Training program development extends beyond technical instruction into cultural changes that challenge decades of American military thinking about air superiority and defensive operations. The Joint Counter Small Unmanned Aircraft Systems Office at Fort Sill now conducts expanded training programs emphasizing rapid decision-making under conditions where traditional air defense procedures prove inadequate. Soldiers learn to operate multiple counter-drone systems simultaneously while maintaining awareness of friendly aircraft operations in the same airspace, creating coordination challenges that require entirely new communication protocols. Operational procedures now assume that American forces will face continuous drone surveillance and periodic attack regardless of mission location or operational security measures. Forward operating bases establish drone defense as the primary mission rather than a supporting capability, with combat operations scheduled around defensive requirements rather than offensive priorities. Supply convoys include mandatory counter-drone escorts, adding complexity and cost to routine logistics operations. Medical evacuation procedures incorporate drone threat assessments that can delay critical patient transport when aerial threats prevent helicopter operations. This transformation represents the most significant shift in American military thinking since the post-9/11 counterterrorism focus replaced Cold War conventional warfare planning. Military leaders trained in air-land battle doctrine and power projection concepts now confront adversaries who can neutralize American technological advantages using commercially available components. Career officers express concerns that traditional American military education may prove inadequate for conflicts where technological superiority provides limited advantages. Technological arms race development focuses on defensive systems that can counter evolving drone threats while maintaining cost-effectiveness ratios that don't bankrupt military budgets. Directed energy weapons research receives priority funding as potentially the only defensive technology capable of engaging multiple small targets simultaneously at reasonable per-engagement costs. Artificial intelligence integration into defensive systems aims to achieve reaction speeds that human operators cannot match when facing swarm attacks. Research and development timelines compress from traditional multi-year cycles into months-long crash programs that sacrifice thorough testing for rapid deployment capabilities. The Pentagon's Replicator program aims to field effective counter-drone systems within 18 months rather than the typical 5-year development cycles for military systems. Military contractors face pressure to deliver working prototypes within quarters rather than years, forcing fundamental changes to defense industry practices. Effectiveness concerns persist despite massive investments and urgent development programs because drone technology continues evolving faster than defensive countermeasures can be developed and deployed. Ukrainian innovations demonstrate monthly improvements in drone capabilities that outpace American defensive system development cycles. The fundamental economic advantages favoring attacking drones over defensive systems remain unchanged regardless of American technological responses. The U.S. military now considers drone swarms a greater immediate threat to overseas bases than traditional missile attacks, particularly in contested regions where adversaries possess advanced manufacturing capabilities and strategic incentives to develop asymmetric warfare systems. This assessment has prompted urgent reviews of defensive strategies across all major theaters of operation, with particular attention focused on regions where potential adversaries might already be developing their own mass-production drone capabilities. China's response and innovation. Beijing's response has been swift and systematic, with military planners studying every aspect of Ukrainian drone operations to develop capabilities that could reshape Pacific power dynamics. Chinese military exercises now prominently feature drone swarm tactics that demonstrate coordination capabilities surpassing anything Ukrainian forces have achieved. Exercise Golden Dragon in January 2025 simulated coordinated attacks against Japanese self-defense force installations, South Korean air bases, and Australian naval facilities using drone swarms launched from disguised civilian vessels. These exercises revealed Chinese capabilities to project drone-based military power across the entire Pacific region without requiring traditional forward-deployed assets. The People's Liberation Army has systematically analyzed Ukrainian combat operations to identify innovations that could be enhanced through China's superior manufacturing capabilities and artificial intelligence resources. Chinese engineers reverse-engineered captured Ukrainian drones to understand modular design principles, then applied these concepts to create weapons platforms optimized for mass production using China's existing electronics manufacturing infrastructure. The most significant advancement involves autonomous target recognition systems that can distinguish between military and civilian assets with 97% accuracy, surpassing Ukrainian capabilities through access to advanced semiconductors and machine learning algorithms. Chinese military strategists have adapted Ukrainian innovations specifically for Taiwan scenarios, recognizing the strategic advantages that short transit distances and mountainous terrain provide for drone operations. The Academy of Military Science released studies examining how coordinated drone attacks could neutralize Taiwan's air defense network within hours of conflict initiation. These analyses consider geographic factors unique to Taiwan operations, including staging areas that provide concealment and operational ranges that maximize drone effectiveness against defensive installations. Manufacturing capabilities represent China's most decisive advantage in developing asymmetric warfare systems that could challenge American military dominance throughout the Pacific. Existing electronics production facilities in Guangdong province can manufacture military-grade drones using established supply chains with minimal equipment modifications. Shenzhen's consumer electronics manufacturers already produce components identical to those used in military applications, creating manufacturing capacity that exceeds any other nation's production capabilities. Chinese planners estimate that converting portions of civilian electronics production to military drone manufacturing could generate monthly output sufficient to maintain continuous operations against multiple adversaries simultaneously. Supply chain advantages extend beyond manufacturing capacity into strategic materials access that ensures continued production despite potential international restrictions. Chinese companies control the majority of global rare earth mineral production necessary for advanced electronics manufacturing, providing resilience against supply disruptions. Domestic semiconductor production capabilities, while limited for cutting-edge processors, prove sufficient for drone applications that prioritize reliability over maximum performance. Integration of civilian and military production lines means that disrupting Chinese drone manufacturing would require targeting civilian infrastructure, creating significant political complications for adversaries. Anti-access area denial strategies developed by Chinese forces specifically target American Pacific defense installations using drone swarm tactics designed to overwhelm existing defensive systems. Military analyses show that coordinated attacks against Guam, Okinawa, and Hawaiian installations could achieve strategic effects using thousands of drones deployed from concealed positions throughout the Pacific. These operations would target fuel storage facilities, aircraft maintenance hangars, and radar installations simultaneously to prevent American forces from conducting effective defensive operations. Chinese planners calculate that successful drone attacks against these installations would require months for repairs, effectively neutralizing American military presence in the Western Pacific during critical operational periods. Regional balance of power implications become apparent through military exercises that demonstrate capabilities specifically designed to counter American alliance structures. Exercise Thunder Dragon showcased advanced drone swarm capabilities with individual units coordinating attacks against simulated enemy positions while maintaining communication through encrypted mesh networks. These demonstrations revealed tactical innovations, including drones that could autonomously reassign targets based on battlefield conditions and swarm formations that adapted to defensive countermeasures without human intervention. Military observers described the demonstrations as profoundly concerning for existing military balance assumptions. Chinese adaptation speed outpaces traditional military development cycles through integration of civilian technology sectors with military research programs. The military-civil fusion development strategy allows immediate incorporation of civilian innovations into military applications, compressing development timelines from years to months. Chinese drone capabilities demonstrated in 2025 incorporate artificial intelligence advances, manufacturing techniques, and electronic warfare countermeasures that were theoretical concepts just months earlier. This acceleration creates a technological development cycle that Western military establishments struggle to match due to separation between civilian and military research programs. Strategic implications extend beyond immediate military applications into fundamental changes in Pacific regional security architecture. Traditional American security guarantees to regional allies assume technological superiority that drone warfare capabilities may neutralize. Chinese capabilities to threaten American installations throughout the Pacific using relatively inexpensive weapons systems undermine deterrence calculations that have maintained regional stability for decades. Allied nations now question whether American military protection remains credible when Chinese forces can potentially neutralize American power projection capabilities using asymmetric weapons that cost fractions of defensive systems. Innovation diffusion from Chinese military programs into civilian applications creates dual-use technology concerns that complicate international arms control efforts. Commercial drone manufacturers in China now incorporate military-grade navigation systems, communication protocols, and artificial intelligence capabilities into civilian products. These technologies provide the foundation for rapid military conversion while maintaining plausible civilian applications that resist export control restrictions. International monitoring agencies struggle to distinguish between legitimate civilian drone development and military capability enhancement programs. China's 2025 military exercises demonstrate drone capabilities that could overwhelm current U.S. Pacific defenses through sheer numbers and coordination sophistication. The mathematical reality shows that American defensive systems designed for traditional aircraft and missile threats cannot engage thousands of small autonomous targets approaching simultaneously from multiple directions. These capabilities have forced other military powers to confront the reality that their most expensive defensive installations may prove inadequate against adversaries willing to embrace asymmetric warfare principles. The implications of this technological shift extend far beyond the Pacific as military establishments worldwide scramble to develop countermeasures against threats that seem to evolve faster than defensive responses can be implemented. Russia's desperate countermeasures. Moscow now faces a defensive crisis that consumes unprecedented resources while failing to protect its most critical assets. Russia has poured billions into Pantsir and S-400 deployments, but still sees drone strikes penetrate strategic bases with alarming regularity. Strategic bomber installations require continuous air defense coverage that drains surface-to-air missile inventories faster than replacement systems can be manufactured. The Plisetsk Cosmodrome maintains round-the-clock electronic warfare operations at enormous cost, yet Ukrainian drones continue reaching their targets. Nuclear weapons storage facilities deploy defensive measures previously reserved for active combat zones, including automated sensor networks extending far beyond traditional perimeters. These extraordinary protective measures reflect the reality that Russian strategic assets face constant threat from weapons that can approach undetected through commercial transportation networks. The defensive systems deployed throughout Russian territory demonstrate mixed effectiveness against Ukrainian drone attacks, with interception rates varying dramatically based on attack profiles and environmental conditions. Electronic warfare installations achieve moderate success rates against older Ukrainian drone models, but prove largely ineffective against newer variants using frequency-hopping communication systems. The Krasuka, for electronic warfare system, designed to counter traditional aircraft and missiles, struggles with small targets flying below radar detection thresholds where terrain masking reduces effectiveness. Russian defensive systems excel at engaging individual targets, but cannot simultaneously track and engage the multiple small signatures characteristic of swarm attacks. Moscow allocated 243 billion rubles toward drone defense programs between 2023 and 2024, representing funds transferred from conventional weapons procurement and maintenance budgets. The investment encompasses 407 companies specializing in counter-drone technologies, artificial intelligence development, and electronic warfare systems. Despite this massive financial commitment, Russian defensive capabilities continue struggling against Ukrainian innovations that incorporate commercial components and open-source technologies that evolve faster than traditional military procurement cycles can respond. Drone threat considerations now constrain Russian military operations to an extent that fundamentally alters strategic planning and tactical execution. Strategic bomber flights require elaborate defensive preparations, including escort aircraft, electronic warfare coverage, and predetermined emergency landing sites equipped with counter-drone systems. Supply convoys moving sensitive materials must coordinate with air defense networks throughout transit routes, creating logistics bottlenecks that reduce operational tempo significantly. Forward military positions face constant surveillance pressure that prevents normal training exercises and limits operational flexibility. Russian commanders report that drone threats influence every aspect of military planning from personnel deployment to equipment positioning. The psychological impact on Russian military leadership manifests through operational paralysis and risk-averse decision-making that constrains strategic options. Defense Minister Andrei Belousov convened emergency meetings with regional commanders throughout 2025 to address defensive failures and coordinate response protocols. Internal communications reveal heated debates about resource allocation between offensive operations and defensive measures. Russian generals express frustration that expensive defensive systems provide uncertain protection while consuming resources needed for conventional military operations. The constant threat of drone attacks creates a climate of uncertainty that affects morale and operational confidence throughout the military hierarchy. Russia confronts significant technological gaps in developing effective countermeasures, particularly in artificial intelligence systems and electronic warfare resistance capabilities. The Digital Sky Initiative represents an attempt to create integrated air defense networks similar to those used by Western militaries, but Russian engineers lack access to advanced semiconductors and machine learning algorithms necessary for sophisticated target recognition systems. Sanctions limiting technology imports prevent Russian developers from accessing commercial components that Ukrainian engineers use routinely. The centralization of drone development under state control constrains innovation by imposing bureaucratic limitations on companies that previously operated with greater independence and flexibility. Domestic production capabilities remain insufficient to match the scale and sophistication of Ukrainian drone manufacturing despite significant government investment. Russian drone production facilities operate at reduced capacity due to component shortages and manufacturing limitations. Quality control problems plague Russian-manufactured drones, with field failure rates significantly exceeding Ukrainian systems that achieve superior reliability ratings. The emphasis on state-controlled development rather than distributed manufacturing networks limits production scaling and technological innovation. Russian military units report consistent supply shortages for counter-drone systems and replacement components needed for maintenance operations. Russia's Doctrine now treats drones as strategic threats on par with missiles. The Kremlin updated nuclear response protocols to consider attacks on strategic bomber bases and nuclear facilities as potential triggers for escalatory responses. Russian military planners now classify drone attacks against nuclear-capable assets as equivalent to traditional strategic threats requiring immediate defensive responses. The Orshnik intermediate-range ballistic missile deployment serves partially as a deterrent signal regarding potential consequences of continued drone attacks against strategic installations. These doctrinal changes indicate that Russian leadership views drone threats as existential rather than merely tactical challenges. Assessment of Russian countermeasure effectiveness reveals persistent vulnerabilities despite massive resource investments and technological development efforts. Ukrainian drone attacks succeed at high rates against defended targets, indicating that Russian defensive systems cannot reliably protect strategic assets. The mathematical disadvantage facing defensive systems becomes apparent when considering that successful attacks require only single drone penetration, while defense requires intercepting every attacking platform. Russian installations demonstrate improved defensive capabilities against predictable attacks, but remain vulnerable to coordinated operations using multiple approach vectors and diverse tactics. The technological arms race between Ukrainian drone development and Russian countermeasures continues favoring attackers who can innovate faster than defensive systems can adapt. Ukrainian engineers push software updates and hardware modifications to deployed systems within weeks, while Russian countermeasure development requires months for implementation. The fundamental economic advantages supporting drone attacks remain unchanged despite Russian defensive investments. Commercial component availability ensures continued Ukrainian access to advanced technologies, while Russian systems depend on domestic production capabilities that cannot match international standards. Russian defensive measures consume enormous resources, yet drone attacks continue to succeed, demonstrating that traditional military approaches cannot effectively counter asymmetric threats. This reality has not gone unnoticed by other actors worldwide who recognize the strategic potential of the proliferation problem. Intelligence agencies now confront a security landscape where sophisticated military capabilities spread faster than traditional monitoring systems can track or contain. The Houthis in Yemen deploy modified Ukrainian-style FPV drones against commercial shipping in the Red Sea, using identical modular design principles and autonomous targeting systems that Ukrainian engineers pioneered against Russian forces. These attacks began appearing in October 2024, just 4 months after Ukrainian operations demonstrated the effectiveness of distributed manufacturing and commercial component integration. Houthi engineers acquired technical specifications through open-source intelligence gathering and reverse-engineered captured drone components to create weapons platforms capable of engaging vessels at ranges exceeding 80 kilometers. The speed of this technological transfer demonstrates how military innovations spread beyond their original contexts within months rather than the years traditionally required for weapons proliferation. Intelligence agencies worldwide struggle to track this technological diffusion because the components and manufacturing techniques appear identical to legitimate commercial activities. Kurdish forces in Iraq utilize Ukrainian drone designs modified for urban warfare, with production facilities operating inside civilian electronics workshops that blend seamlessly with normal commercial operations. Syrian opposition groups manufacture similar systems using components smuggled through Turkish supply networks that handle both civilian and military electronics simultaneously. Mexican cartel organizations represent perhaps the most concerning example of Ukrainian drone technology proliferation beyond traditional conflict zones. The Jalisco New Generation Cartel deployed autonomous attack drones against rival groups in Michoacan during January 2025, using weapon systems nearly identical to those attacking Russian installations. These drones incorporated the same frequency-hopping communication protocols, modular payload attachments, and artificial intelligence targeting algorithms that characterize Ukrainian military systems. Cartel engineers access technical specifications through encrypted forums and dark web marketplaces where Ukrainian innovations are shared without restriction or oversight. The fundamental shift in asymmetric threat capabilities becomes apparent when examining how small groups now possess military capabilities previously limited to nation-states. A workshop in Somalia produces maritime attack drones using Ukrainian design principles to target commercial vessels transiting critical shipping lanes. Pakistani separatist groups manufacture similar systems for operations against government installations in Balochistan. These organizations operate with budgets measured in thousands rather than millions of dollars while achieving military effects that would have required conventional forces costing billions to develop and deploy. Commercial availability of necessary components ensures continued proliferation regardless of export controls or international restrictions because the same technologies serve legitimate civilian applications. Smartphone processors provide sufficient computing power for autonomous targeting systems. Consumer cameras offer adequate resolution for target recognition algorithms. Commercial GPS modules deliver navigation accuracy sufficient for precision attacks. Electronic speed controllers designed for racing drones provide flight control capabilities identical to those used in military systems. This dual-use nature means that restricting access to military applications would require banning entire categories of consumer electronics. Myanmar's military junta deployed Ukrainian-inspired drone swarms against ethnic minority populations in Rakhine State during February 2025, marking the first documented use of these weapons systems in genocide operations. The drones incorporated identical targeting algorithms and swarm coordination protocols while carrying incendiary payloads designed to destroy civilian infrastructure. International observers documented attacks that followed tactical patterns directly copied from Ukrainian operations, including multi-vector approaches and electronic warfare countermeasures. The proliferation extends beyond active conflict zones into potential terrorist applications that concern counterterrorism agencies worldwide. European intelligence services intercepted communications indicating that multiple extremist organizations are attempting to acquire Ukrainian drone technologies for potential attacks against civilian targets. The modular design principles that enable rapid battlefield adaptation also facilitate conversion to terrorist applications using identical technical approaches. Law enforcement agencies struggle to distinguish between legitimate drone hobbyists and potential terrorist activities, when both groups use identical components and similar technical knowledge. African conflict zones demonstrate rapid adoption of Ukrainian innovations adapted to local conditions and operational requirements. Forces in the Democratic Republic of Congo utilize modified Ukrainian designs for operations in dense jungle environments where traditional military systems prove ineffective. Libyan militias incorporated these technologies into urban warfare scenarios around Tripoli and Benghazi. Ethiopian federal forces deployed similar systems during operations in Tigray region. Each adaptation incorporates local modifications while maintaining core Ukrainian innovations in autonomous operation and swarm coordination. The manufacturing democratization enabled by Ukrainian innovations means that weapons production no longer requires traditional defense industrial capabilities or significant capital investments. A facility in the Philippines produces combat drones using 3D printers and electronic components purchased through normal commercial suppliers. Lebanese groups manufacture similar systems in workshops that double as consumer electronics repair services. These production capabilities can be established quickly using readily available equipment and provide output sufficient to support ongoing operations while remaining virtually undetectable to traditional intelligence monitoring methods. Software proliferation presents additional challenges as artificial intelligence algorithms and control systems spread through online repositories that serve both civilian and military applications. Ukrainian software developers publish drone control algorithms on GitHub and similar platforms where they appear alongside legitimate civilian drone applications. These programs include advanced features like swarm coordination, autonomous targeting, and electronic warfare resistance that can be adapted for military use without modification. Training requirements for operating these systems remain minimal compared to traditional weapons platforms, enabling rapid capability development by groups with limited technical expertise. Online tutorials demonstrate assembly procedures using widely available components. Simulator software allows operators to develop piloting skills using consumer gaming equipment. Technical support communities provide troubleshooting assistance and design improvements through encrypted communications channels. The economic advantages that favor drone warfare over traditional military systems apply equally to non-state actors who benefit from cost-effectiveness ratios that make sophisticated capabilities accessible to organizations with modest budgets. Criminal organizations achieve strategic effects using investments measured in thousands of dollars rather than the millions required for conventional weapons systems. At least 12 different conflict zones now feature drone tactics directly inspired by Ukrainian innovations, creating a security environment where advanced military capabilities no longer remain confined to nation-states, but spread rapidly to any group with access to commercial electronics and basic technical knowledge. This proliferation creates an unprecedented challenge for military establishments worldwide who must now defend against threats that can emerge from virtually anywhere while operating under economic constraints that favor attackers over defenders. The defense dilemma. Military establishments worldwide now confront a mathematical impossibility that threatens the foundation of modern defense strategy. Every defensive system faces the same brutal reality. Intercepting one attacking drone costs between 100 and 10,000 times more than producing that drone. The U.S. Navy discovered this equation firsthand when the USS Carney fired a $2.1 million Standard missile, to destroy a $500 Houthi drone in the Red Sea. This single engagement illustrates the fundamental economic imbalance that makes traditional defensive approaches unsustainable against mass drone attacks. Defending against drone swarms requires simultaneously tracking and engaging dozens or hundreds of individual targets approaching from multiple directions at varying altitudes and speeds. Current air defense networks can process approximately 20 to 40 simultaneous tracks depending on system configuration and operator training levels. Ukrainian drone swarms routinely deploy 200 to 400 attacking units in coordinated operations that overwhelm defensive tracking capabilities within minutes of engagement initiation. The mathematical impossibility becomes apparent when defensive systems designed for sequential engagement face simultaneous threats exceeding their processing capacity by orders of magnitude. Traditional air defense systems operate on design assumptions that prove counterproductive against small, numerous targets flying at low altitudes. The Patriot missile system achieves exceptional performance against ballistic missiles. An aircraft but struggles with targets smaller than motorcycles approaching at treetop level. Radar systems optimized for long-range detection of large signatures cannot reliably distinguish between attacking drones and background clutter, including birds, vehicles, and atmospheric interference. The S-400 system demonstrates similar limitations when attempting to engage multiple small targets simultaneously, achieving interception rates below 30% against coordinated drone attacks despite costing $500 million per battery. Detecting small aerial targets presents technical challenges that existing radar technology cannot overcome through software updates or calibration improvements. Drones operating below 150 meters altitude disappear into ground clutter that makes radar identification nearly impossible using current detection algorithms. Weather conditions including rain, snow, and atmospheric turbulence create false returns that overwhelm human operators attempting to distinguish genuine threats from environmental interference. Urban environments compound these difficulties through electromagnetic interference from commercial communication systems and physical obstacles that create radar shadows where attacking drones can approach undetected. Current counter-drone technologies face fundamental scalability limitations that prevent effective deployment against coordinated swarm attacks. Electronic warfare systems can jam individual drone communications but lack sufficient power output to disrupt hundreds of frequency-hopping targets simultaneously. Kinetic interceptors like the Raytheon Coyote system cost $85,000 per round and require direct hits against maneuvering targets smaller than automobiles. High-energy laser systems demonstrate impressive capabilities against single targets but require perfect atmospheric conditions and consume enormous electrical power that limits sustained operations. Development timelines for effective counter-drone systems extend years beyond the pace of offensive drone evolution, creating permanent technological disadvantages for defensive forces. Military contractors require 36 to 60 months for developing, testing, and fielding new defensive systems through traditional procurement processes. Ukrainian drone capabilities advance monthly through rapid prototyping and field testing that incorporates lessons learned within weeks of combat operations. Russian defensive systems deployed in 2025 counter threats from 2023 while facing Ukrainian innovations that incorporate 2 years of additional development and battlefield adaptation. Resource constraints limit defensive system deployment to protecting only the most critical installations while leaving secondary targets vulnerable to attacks that can achieve strategic effects. The Pentagon estimates that comprehensive drone defense for all overseas military installations would require $240 billion in initial equipment costs plus $85 billion annually for operations and maintenance. These figures exceed entire annual defense budgets for most NATO countries and represent funds unavailable for offensive capabilities, training, or conventional weapon systems. Current defensive systems would need to be 100 times more cost-effective to economically counter modern drone swarms. This mathematical requirement represents improvements far beyond anything achievable through incremental technological advancement or increased defensive spending. The speed of light constrains laser weapons' effectiveness in adverse atmospheric conditions. Electronic warfare faces physical limits on power output and frequency coverage. Kinetic systems require ammunition supplies that become logistical vulnerabilities during sustained attacks. The implications extend far beyond technical limitations into fundamental questions about military strategy and international security. Traditional military doctrines based on controlling territory and airspace collapse when adversaries can threaten defensive positions using weapons costing fractions of defensive countermeasures. Forward operating bases that enable global military presence become liabilities when defensive costs exceed operational benefits. The mathematical reality favors asymmetric attackers who exploit economic and technological advantages that defensive forces cannot match. This defensive crisis represents more than a temporary tactical challenge requiring new equipment or updated procedures. The fundamental shift in military economics has created permanent advantages for attackers that no amount of defensive investment can overcome. Military strategists now recognize that traditional approaches to warfare may prove obsolete within the current decade, forcing complete reassessment of how nations project power and maintain security in an environment where technological democratization has eliminated historical military advantages. The future of global conflict. Military strategists at the RAND Corporation published assessments in late 2024 predicting that traditional military hierarchies will collapse within the next decade as drone technology democratizes warfare capabilities across all levels of conflict. These analyses examine scenarios where individual soldiers equipped with drone swarms can achieve tactical effects previously requiring entire battalions of conventional forces. The implications extend beyond battlefield tactics into fundamental questions about military organization, command structures, and resource allocation that have defined armed forces for centuries. Career military officers trained in conventional warfare doctrine now confront the reality that their expertise may prove irrelevant when facing adversaries who can neutralize traditional advantages using commercially available technology. The established order of military power based on expensive platforms, complex logistics, and extensive training programs faces systematic disruption from technologies that bypass these traditional requirements entirely. Small nations previously dependent on major powers for security guarantees can now develop indigenous capabilities that rival or exceed those of traditional military superpowers. Estonia's recent procurement of 10,000 commercial drones modified for military applications provides defensive capabilities that would have required billions of dollars in conventional weapon systems. Similar programs in Latvia, Lithuania, and Slovenia demonstrate how countries with modest defense budgets can achieve strategic deterrence through asymmetric capabilities rather than expensive conventional forces. Non-state actors present the most dramatic example of this military democratization as organizations with annual budgets measured in millions rather than billions now possess capabilities that can threaten nation-state military assets worth hundreds of times their total resources. Kurdish forces in Syria demonstrate tactical innovations using drone swarms that surpass capabilities available to most NATO militaries just 5 years ago. Mexican cartels deploy surveillance and attack drones across territories larger than many European countries, creating operational challenges that conventional military and law enforcement approaches cannot address effectively. This capability diffusion represents a permanent shift in global power dynamics where traditional military advantages provide diminishing returns against adaptive adversaries using innovative approaches. Technological obsolescence threatens military systems that require decades and trillions of dollars to develop, as relatively simple innovations neutralize sophisticated defensive networks through economic rather than technical superiority. The U.S. Navy's $13 billion Gerald R. Ford aircraft carrier faces potential neutralization by drone swarms costing less than a single F-35 fighter aircraft carried aboard the vessel. Russian S-400 air defense systems, representing decades of engineering advancement, prove inadequate against coordinated attacks using drones assembled in civilian workshops. Chinese military installations defended by advanced radar networks and automated defensive systems remain vulnerable to attacks launched from concealed positions using technologies available to civilian hobbyists worldwide. International security frameworks established during the Cold War assume military capabilities remain concentrated among major powers with sophisticated defense industries and extensive technological resources. These assumptions collapse when confronting adversaries who achieve strategic effects using distributed manufacturing, commercial components, and open-source designs that eliminate traditional barriers to military capability development. Arms control agreements focused on limiting production of specific weapon systems become meaningless when identical results can be achieved using components available through normal commercial channels. Traditional intelligence gathering methods prove inadequate for monitoring threats that emerge from civilian infrastructure and blend seamlessly with legitimate commercial activities. Military planners worldwide struggle to adapt institutional approaches designed for predictable threats with known capabilities to environments where adversaries can rapidly develop new tactics using readily available technologies. The Pentagon's 2025 budget allocates $240 billion toward traditional weapon systems while dedicating only $8 billion to counter-drone technologies, reflecting institutional priorities that may prove strategically irrelevant. Other militaries, such as China, study Ukrainian innovations to inform their own UES doctrines, as noted by size. Russian military planning continues prioritizing nuclear deterrence and conventional forces despite facing daily attacks from adversaries using asymmetric approaches that bypass these expensive capabilities entirely. Professional military education systems require fundamental restructuring to address warfare realities that differ dramatically from scenarios that dominated military thinking for decades. Staff colleges teach campaign planning based on assumptions about force ratios, logistics requirements, and technological advantages that drone warfare renders obsolete. Military academies emphasize leadership principles developed for managing large conventional units, while future conflicts may involve small teams operating autonomous systems that require completely different command approaches. Officer career development paths prioritize experience with expensive conventional systems that may provide limited relevance for conflicts dominated by asymmetric capabilities and technological innovation rather than traditional military expertise. The threshold for armed conflict continues lowering as military capabilities become accessible to actors previously limited by resource constraints and technological barriers. Regional disputes that remain diplomatic because military options were prohibitively expensive now present kinetic possibilities for parties with modest resources and technical capabilities. Criminal organizations can potentially challenge government authority using military-grade capabilities rather than small arms and improvised weapons. Terrorist groups gain access to precision strike capabilities that could threaten critical infrastructure and government installations previously protected by geographic distance and defensive systems. This accessibility fundamentally alters conflict calculations by expanding sophisticated military options to actors across the spectrum of international relations. Strategic unpredictability emerges from environments where military capabilities can be developed rapidly by unknown actors using methods that resist traditional intelligence monitoring and international oversight. Intelligence agencies designed to track state-sponsored weapons programs struggle against threats that emerge from civilian infrastructure and operate through commercial supply chains. Military planning processes that require months or years for implementation face adversaries who can develop and deploy new capabilities within weeks using rapid prototyping and commercial manufacturing resources. Traditional deterrence calculations based on known adversary capabilities become meaningless when potential opponents can rapidly acquire new military technologies through approaches that provide no warning indicators to defensive planners. Military experts now predict that by 2030, drone swarms will be the primary determinant of battlefield outcomes. This assessment reflects mathematical realities favoring distributed, inexpensive systems over concentrated, expensive platforms that have dominated military thinking since World War II. The transformation has already begun, and its effects will reshape global security calculations for decades to come. What we're witnessing represents more than tactical innovation or temporary technological advantage. Ukraine's drone revolution has upended military balance worldwide, forcing every defense establishment to rethink strategy in terms of manufacturing warfare rather than traditional platforms. The June 2024 attacks proved that $600 drones could neutralize billion-dollar strategic assets, creating cost-effectiveness ratios that make conventional defense economically impossible. This isn't temporary tactical adaptation, but permanent transformation, where commercial electronics enable strategic military effects previously requiring nation-state resources. Military planners from Washington to Beijing now confront mathematical realities where defensive systems cost thousands of times more than attacking platforms. The democratization of precision strike capabilities means critical infrastructure everywhere faces threats that emerge from civilian supply chains and resist traditional countermeasures. If you found this analysis valuable,